Welcome back to the lab. Welcome back to EE for everyone. Today we're going to talk about all the changes that we want to make between the Proto 1 and the Proto 2 electronic load. This could be a long one, so grab a fresh cup of coffee, settle in, and let's get started. The first place that we need to go is thermal management. Like I said, thermal management. Yeah, so we're not messing around this time. We are really not messing around. We've got the Hyper 212 Evo. It's not the craziest CPU cooler in the world, but it is certainly no slouch. It's got 4 heat pipes, and what I specifically like about this one is that they grind the heat pipes to make direct contact with, well, what's normally a CPU. In this case is our MOSFET. This thing has got some heft to it. It should do a great job of keeping it cool, but it's kind of big, it's kind of heavy, and honestly, I don't know if this fin stack is going to be enough. I really don't know if that's going to keep our FET cool enough. We've got a little backup plan. First of all, we need these shims, copper shims, to couple our FET to the PCB well thermally for our over temperature protection, but I've got a couple of these as well, and yes, I do mean a couple. These are water cooling radiators meant for use in, well, water cooling systems. I think we've told you that before. Yes, we're using a LG115X mounting bracket. That's why we're doing this, and so we're going to have a water loop with one or maybe more than one electronic load and one or more than one water cooling radiator. So I'm very excited to see how this all works out. After all, we are trying to dissipate thousands of watts of power, and that's really the core of it, right? We need to make sure that we can get the heat out of our part and into the room fast enough, efficiently enough, and I'm hoping that that air cooler will be a good place to start when we're doing our initial testing, get an idea for how hot this thing gets, and then later on we will really push the limits of what is possible with the water cooling. I can't wait. I'm super excited to see how this all turns out. I have never successfully burned this much power in a box before. Not for a lack of trying. Check out our previous series, the UPS project, Phase 2 UPS project. We certainly tried. Well, actually, that wasn't even, no, we were trying to push 2,000 watts through that box. Now we're trying to burn 2,000 watts in this box. That is a totally different animal. Okay, but that is not the end. Thermal limiting is another one that we had to do over temperature protection. I alluded to it. Basically, I've got these copper shims. We could have just used shims, FR4, really anything, but I got this copper plate, which will add some thickness. The FET isn't quite exactly the thickness of a CPU socket plus the integrated heat spreader and all that stack. It's not quite the same. Unfortunate that it's not. So we're going to attempt to solder pieces of this copper plate onto the PCB and then put a thermal pad on top of this, just like there will be on the bottom. That's the intent. Hopefully it works out. Guess we'll see. That will allow us to basically save the FET from an operator. Let's say, for example, someone decides to hack their electronic load and they try to push the power a little higher than they should by removing the limiting. There's literally a pound to find to, I know what I'm doing, I've changed the cooling, I know this is better, let me get as much power out of this FET as I can. So if you want to get like a sub-zero cooling solution and pull 2,000 watts out of the thing, whatever, go ahead. Anyways, voltage measurement, we've made some changes here too, and these are more theoretical. The biggest change that we've made up front is adding more resistors because the power dissipation was a little high. Why is the power dissipation high? Well, because we want to keep the impedance low as we can to maintain accuracy of that voltage measurement. Honestly, I'm not sure why it was as bad as it was. We implemented the voltage ADC and the current ADC with fundamentally the same circuit, and just one of them works great and the other one doesn't. Might add a bigger capacitor here, might try to add even lower resistance, and that's why we've got 4 geometries here, so we can really play around with it and push it to where it needs to be. So I guess, yeah, I know it needs to change, and we didn't change much, unfortunate. But the current measurement, we did change a lot here. Basically, we added another op amp, though we tried to reduce that number. We added another op amp. So instead of doing the error amp and the gain in one stage, we are now going to amplify the current measurement, which will also help with the transient tolerance, because now this is a plus or minus 15, plus or minus 8-ish volt rail. And there's a much larger range of voltages allowed for that fault voltage before we'll start to damage anything, which is great. So basically what we're going to be measuring now, instead of measuring millivolts, we're going to be measuring volts, where 3 volts is 10 amps on the output instead of, I think it was, I don't remember, it was a small voltage before. All right, then on top of that, we can see that clearly, right, we've got the water cooling radiator standard components for computers. We've got a lot of modular cooling, a lot of standard industry standards that we're trying to comply to. Well, took a little page out of our book from the UPS project, and we designed the mainboard that will allow for controlling up to 4 of these front ends. Basically passes through the power to the board and sends the control signals through. That mounts with the standard ATX footprints. We can use a normal computer chassis to house it. That allows for mounting our water cooling radiators, etc., etc. Fans, cooling, great, awesome. But we took it one step further, and we went for a power supply, a standard ATX power supply. You might notice this is not a name brand. Well, maybe it is. I don't know. It looks like they want to be a name brand, but it's not. This is not a Corsair. This is not a PowerSonic. This isn't a EVGA. This isn't any of them. And why? Why not? Well, because there weren't any available. Man, sourcing electronics from China got really weird when this whole virus thing happened. So this is what we could find. This is what we could get in the shop soon enough. And I mean, it's not too bad, right? They're all basically made from the same parent company, so hopefully this one's all right. We're going to use the ATX 24-pin connector to get the power into the electronic load mainboard, and then we will break it out from there. More to come in the future videos. The power supply will mount where the power supply goes in the computer chassis, the water cooling radiators where the radiators go, the fans and so on. It's just everything has its place, and we didn't really need to build it because that is how this works. Now, I freely acknowledge that a few water cooling radiators, pump, reservoir, tubing, water blocks, big motherboard, and it's gonna be a little expensive, and that's not really the vision that I have for our community edition electronic load. I think something more this form factor with a single output and a smaller micro and just generally higher level of, one board solution is going to be a little better. I think that's going to be better for the people in our community. And so this is ultimately what I want to do for you. Now, with that said, I really don't know what's going to be best for our community edition electronic load. I don't know if it will be better to use this standard daughter card format so that if somebody wants to design their own daughter card, they can just drop it in and take advantage of the processing, right? If you want to build your own front end, upgrade the power, make it a switch mode stage. I don't know what you want to do, but if you want to do something like that and you still want to control it the way that we're controlling this, maybe you would like to have the daughter card. Maybe you'd rather just have it built the way it is and get the ratings and use it like that. I don't know. Let me know in the comments what you think. Do you want to be able to design your own front end for higher voltages, higher power, or maybe both? Do you want to be able to make it higher accuracy, or I don't know. Let me know. Let me know your thoughts in the comments. And that might shape what our community edition electronic load looks like. All that said, I'm so excited for Proto 2, and I hope that you can tell. I'm excited to see what our Proto 2 electronic load can do. And yeah, just make sure that you're subscribed so you get to watch what happens when we integrate all this stuff, build up this incredibly complex system, and just have a little bit of fun in the shop trying to burn a couple thousand watts and get the heat out of these 1 to 4 components. If you like this video and you can't wait for more, let me know by hitting that like button or leaving a comment down below. If you'd like to support the channel, consider checking out the Patreon page linked in the description. It really helps out a lot. Thank you. Thank you to everyone who's taken that step of supporting us directly. But really, I'm just thankful for everyone that supports us in any means. Most of all, I hope that you learned something great today, and I hope to see you again soon. Thank you for watching EE for Everyone, and thanks for staying till the end. Bye. I can't wait to mount this giant cooler onto our MOSFET. I can't wait. This is going to be fantastic.